Okay, hi everyone, and I would like to thank Ricardo and Elliot and Wenbin for giving an introduction to this topic. So I'll be presenting mostly a model that Brian and I have been working on, and some additional implications and connections to other thoughts regarding repeating nuclear transients and QPEs. So this is just a quick reminder of the observational properties that we've heard about these sources. So we've just seen that, so I'll skip it. And I will focus on some kind of important observational clues that maybe were not highlighted as much, which include the clue that comes from the timing of the flares, this QPE TDE association and what that might imply for a theoretical model for these sources, and then this discussion of rates and abundances. So we have a handful of QPE systems, and in some of them, we have this very typical behavior that the timing between consecutive flares seems to alternate between long and short. So say 9 hours, 10 hours, 9 hours, 10 hours. So this is, for example, seen here in GSN 069, showing the time between consecutive flares that is alternating back and forth, also in EuroQPE2, and these deviations of order 10%. So this quasi-periodicity in some cases is actually quite regular. There are also other sources like EuroQPE1, which seems to have more erratic timing of the flares. This clue will be important in the model I'll be discussing. And another clue that was reviewed very nicely by Ricardo is this QPE TD association. So even if we are not quite certain about whether, in GSN 069, prior to the appearance of QPEs, it was actually a TDE, we do know that we've seen this gradual X-ray decay over the course of a few years, and there is some indication of kind of a similar overall behavior in other systems. And we also know that the hosts are possibly also consistent with what we know about TDE hosts. And lastly, we know that QPEs are intrinsically rare. So this is, again, discussed by Ricardo, but just to repeat this argument, we have a handful, or in the case of Rosetta, we have 4 QPEs. We can consider the distance up to which they were observed, how many galaxies of relevant mass are there within this volume, and use that to estimate the rate or the abundance. So we know that there is roughly 1 QPE per 10 to the 4 or 10 to the 5 galaxies. And this could be translated into rate, but it's obviously degenerate with the mostly unknown lifetime of QPEs. So we only have a handful of systems, and we haven't seen any QPE appear and disappear, so we can only say very roughly that perhaps they last a decade, maybe more, but that will translate into an assumption about their rates. So as we've heard, there have been quite a lot of models that have been proposed in the last few years for QPEs, and Wenbin has also mentioned this dichotomy between different models. And I will be discussing this star-disk collision model that we've worked on. And before that, I'll just mention that kind of it's good to keep in mind this dichotomy between 2 different ways in which stars might be destroyed near supermassive black holes. So we've mostly heard this week about this channel where a star plunges towards the supermassive black hole on a nearly radial orbit, and this process is mostly governed by scattering or relaxation in angular momentum of stars at the outskirts of the radius of influence around the supermassive black hole. But then perhaps a less dramatic effect, but might be relevant for QPEs and these other sources, is this analogous case where we have this, what we call a stellar emery. So a star that approaches the supermassive black hole through the emission of gravitational waves, maybe up to the point that it reaches the tidal radius and starts to shed mass, or maybe something else happens to it before. But I will be focusing on these stellar emeries, which we believe are important for QPEs. So about a year ago, over the course of 1 week, So there were 3 papers, ours and a paper by the group from Milan that was led by Alicia, who's sitting here in the audience, and another paper by Hiromichi Tagawa and Zoltan Hyman. And we all proposed a similar idea regarding what might cause QPEs. So I think that was also very nice to see that different theorists independently arrived at kind of a similar picture as to what might cause them. I think this is kind of reassuring that there's some convergence on these different theoretical ideas. But I'll also point out that we all avoided posting an archive on April 1st. So that was kind of an important time constraint at the time. Okay, so this cartoon kind of sketches out the basic picture. So what we have is a supermassive black hole that is engulfed by an accretion disk. And we have this stellar emery on an inclined orbit relative to the disk. So the star passes through the disk twice per orbit. And the collisions between the star and the disk produce a flare, which is a shock-heated disk material that expands both above and below the plane of the disk. So the flares comes from this shock-heated material that expands and cools, and the quiescent emissions comes from the inner radius of the disk, producing these soft X-rays that we've seen. Obviously, the timing of the collisions will be subject to the precession of the orbit, possibly the precession of the disk, and I will be discussing different aspects of this model and why we think it can explain, at least qualitatively, the observations. So I've mentioned that we have this flare both above and below the plane of the disk, and kind of as a terrestrial example, you can think of this bullet passing through an apple where you get ejecta going in both directions when this shock-heated material searches for a path of least resistance. So some material is pushed ahead and some might be thrown backwards. Okay, so one kind of obvious thing that this model explains is this dichotomy of this long-short alternating recurrence time. Right? So if we have this star on a slightly eccentric orbit, the timing between collisions will be shorter as the star passes through pericenter and slightly longer as it passes through apocenter. The exact timing will depend on the relative orientation of the orbit with respect to the disk. But for a general configuration, this deviation in timing will be comparable to the eccentricity. So as I mentioned before, these deviations of order 10%, which amounts to an eccentricity of about 0.1, which I may mention later why we think is actually reasonable given the formation scenario we propose. I'll also mention out that in Alicia's paper, they've taken this one step further and considered the rigid body precession of the disk itself, and have shown that one could produce even a more complex timing of flares subject to these different precessional effects. So I think once we actually want to do a proper modeling of the timing of the flares, this will be important. And I'll also point out, and this will probably be discussed by Johin, that this has been done to some extent in EO QPE1, showing that we may actually see signs of these different precessional modes in the timing of the flares for this system. Okay, so how do we actually get the flares? So we have a star passing through the disk, and it shock heats this cylinder of disk material with its own geometrical cross-section. I should mention that there isn't any significant gravitational focusing because the collision is so supersonic. And as we've heard from Elliot, there's also a possibility that actually after several such collisions, there is kind of a bigger cloud of ablated material that comes along with the star. So possibly this cross-section is enhanced due to that. But then you can consider how much mass is being swept by the star, what is the energy that is deposited into this shock-heated material. And then in terms of the velocities, the shock velocity will be comparable to the Keplerian velocity. And for these relevant periodicities that we're seeing of order hours, this is a fraction, about 0.1 of the speed of light. Okay, so how do we produce the radiation? So initially, this shock-heated material is very optically thick. So it has to expand quite a bit before it can radiate. So the condition for the photons to escape is when the diffusion time becomes comparable to the dynamical time of this expansion. And that gives you this famous criterion for the optical depth. It has to go down to roughly C/V. So that sets the diffusion time over which this flare should rise. So that amounts to roughly a fraction of an hour. Maybe the duration of the flare itself will be a couple of times this diffusion time. Maybe it will set by the time over which this debris that Elliot has mentioned arrives. And then the luminosity is given by the remaining internal energy accounting for the adiabatic degradation of the internal energy emitted over this time. So that gives you luminosities in the right ballpark. As for the temperature, this is a bit of a subtle point, but we actually think that there is not enough time for photons to be produced as the star passes through the disk to actually achieve thermalization. So we think that the emission is slightly non-thermal in the sense that what we are seeing is the Bremsstrahlung photons that are being produced as the star passes through the disk. And we estimated it, but this is still with a bit of a question mark, that this process could produce flares with temperatures of 100 electron volts, which is what is needed to explain the observations. I'll also point out, so Ricardo has shown us that QPEs, by definition, so it turns out, have this typical behavior in the temperature luminosity plane. This is essentially a reflection of how the different bands rise and decay. And you can kind of compare that qualitatively to what one obtains in the context of supernovae explosions, which are essentially a similar process. You have shock-heated material that expands and radiates. So this will generally depend on the energy deposition within this ejecta, but qualitatively, you'll also get this behavior where the harder bands rise faster than the softer bands. Okay, so what is the origin of the disk? So we heard from Elliot before, 3 possibilities, so I'll just review them. So we just heard in detail from Wenbin now about option 1, which is that the disk is self-fed by the star. Okay, so the disk is formed by the star itself, and the star interacts with this disk. So this could be through stripping related to this ablational process, or through Roche lobe overflow at pericenter, where the star sheds mass and produces this disk. Another option that has been explored is perhaps this disk is some pre-existing extended AGN disk. And the option that we opt for is that the disk is actually the result of a separate star undergoing a TDE in the same system. So this has led us to choosing this title for our paper, that EMRI plus TDE equals QPE. And the idea is as follows. So if you have this stellar EMRI on a relevant orbit that will be required to produce the QPEs, so 10 or so hours sitting around the supermassive black hole, it will hang there for around 1 million years. That's the gravitational wave timescale. And we also know that in a typical galaxy, the rate of TDEs is such that every 10 to the 4 years or 10 to the 5 years, we expect a TDE to occur. So if we have this EMRI hanging out there, a TDE will occur during its in-spiral time, granted, and then this TDE will eventually form a compact accretion disk with which the EMRI that was already there will now interact with and potentially produce flares. So this picture obviously explains this association between QPEs and TDEs. Why do we see QPEs following TDEs? The delay time between the TDEs and the QPEs may be related either to the time that it takes the disk to actually form and settle, or perhaps if the EMRI is on a somewhat wider orbit, the disk should spread until the EMRI could intercept it. It also explains why we're seeing periodicities of order hours. So that has to do with the fact that the orbital period at the tidal radius is by definition close or some constant times the dynamical time of a star. So we naturally get this hour time scale for the periodicity. I'll say a few words about the formation. One kind of useful way to think about these processes in centers of galaxies is in this phase space diagram, where this is the pericenter distance of possible orbits around the supermassive black hole, which is a proxy of the angular momentum. And this axis is the semi-major axis, which is related to the energy. So circular orbits are along this diagonal and nothing is around here. So most stars within the nuclear star cluster are located at around the radius of influence on mildly eccentric orbits. And then two-body scattering or other relaxational processes might lead to diffusion in this phase space. And it turns out that once an orbit becomes eccentric, its relaxation time in angular momentum becomes shorter than the relaxation time in energy. So the trajectories typically look like you start to diffuse and you go up and down along this line with a fixed energy but with varying angular momentum until you occasionally approach the loss cone and undergo a TDE. So that's kind of a toy model picture of how TDEs occur. But if you start out with a smaller semi-major axis, you initially first diffuse up and down, but then you hit this green line, which is where gravitational wave dissipation timescales become shorter than this diffusion time, and you start to circularize towards the supermassive black holes, and that's how we think these stellar emeries are formed. Actually, as was pointed out, possibly the injection of stars towards these relevant orbits might be dominated by the Hills mechanism, so I think this is kind of the process that produces these stellar emeries. And then one can discuss the rates. So the rate of TDE is essentially dictated by the bottleneck at the radius of influence. So it's the relaxation time at the radius of influence that sends stars onto these highly eccentric orbits. So you can show that this is actually related to the orbital period at the radius of influence. So that gives you this famous 1 TDE per 10 to the 4, 10 to the 5 years. So for the Hills mechanism, one can naively estimate that this is essentially related to the TDE rate times the fraction of binaries within the radius of influence. So for 10% binaries, one gets maybe one formation of such an emery every 10 to the 5 or 10 to the 6 years. And as was pointed out by Elena, we have now direct constraints perhaps on this process in our own galaxy by analyzing the rate at which hypervelocity stars are formed. I'll also point out that if you combine this formation rate with the time that stars spend around these relevant orbits, you actually get that they're not that rare. So possibly every galaxy has order unity such star on a relevant orbit waiting there until perhaps a TDE occurs. So I think this question of how many TDEs are actually followed by QPEs is related both to this value, but then also to the question of whether a single emery can survive multiple TDEs or not. How much time do I have left? Okay, I'll be quick. So just, I'm not sure if, as Wenbin mentioned, if the observers are working hard enough or not, but we asked ourselves the question of could there be analogs to QPEs in other bands. This is mostly motivated by Ultrasat, which will be launched in the next few years. And we showed that under some conditions, the same process that I described could actually produce UV flares that will outshine the disk emission. So usually the X-ray QPEs, we see them because the veen tail of the flare emission outshines the veen tail of the disk. But in some conditions, the flares can actually peak in the UV. And then with the right conditions, you might have an observable UV flare. Okay, I think I'll skip this. And maybe I'll point out that we also heard about some other repeating nuclear transients. So Sassian 14KO is as an interesting example where we have exquisite timing of the flares, and we are seeing even a period derivative in this system. And in a recent paper with Elliott, we considered different processes that could lead to this period evolution, and we concluded that one possible mechanism would be the interaction of such star with a pre-existing AGN disk that will dissipate its orbit. So this is in a sense kind of an interesting concept that could also be applied to QPEs, where these orbiters could be used as mechanical probes of the disk conditions measuring this dissipation rate. Okay, and I think I'll just mention this point that we already heard about ablation of stars as they pass through disks. And this could also be an interesting way to explain perhaps the variability in quiescence that we were seeing in these different sources. And I think I'll finish with this and take questions.
Thanks. Really, really nice talk. I just have kind of a two-part question. The first one is, so you kind of focus very much on the TDE disk scenario. Is there any reason why an AGN disk would not work in this model? And the second part of the question is, if an AGN disk can work, if you expect such a high rate of MREs, would we not expect to see QPEs in most AGN?
Yeah, those are great questions. So part of the motivation for considering TDE disks is indeed to explain this association that we were seeing between TDEs and QPs. You could in principle think of an AGN disk as an alternative for the disk with which the star interacts. But the problem is that AGN disks are long-lived. So during the process that has brought this star from far out in the radius of influence towards this small orbit, the star would have needed to interact with this disk way before. And we saw earlier that these star-disk interactions could actually be quite harmful for the star itself. So it's not clear that the star could survive kind of a long-lived phase of an AGN disk without being destroyed prior to getting to these short orbits. Maybe in some conditions the star could perhaps be saved by becoming embedded in the disk, so it will be within the plane of the disk and will not undergo these collisions, and then will be migrated. Perhaps the AGN then dissipates, and then perhaps it will be on an orbit that could produce QPEs with a TDE. But I think this is still kind of an interesting topic to study, but we disfavor AGN disks because of the reasons that I mentioned.
Thanks.
Ricardo, I guess. Okay, first I want to apologize for not working very hard, but I'll be better. Second, can you go back to slide 19? Yeah, so effectively to convert these two rates,
Yeah.
I guess you're doing some probability estimates as to where the stars are in a given nucleus. Like, have you made like a 2D map of where a reasonable cluster of stars and compact objects would be in a given moment in a galaxy, and what the what the resulting range of RPA or periods would be as the most likely distribution for a solar mass star?
Yeah.
Because then one could tie it to viscous models for accretion disk with, and you could say, what's the period that I would reach, or what's the RPA that I would reach within 10 years with a TDE disk? And then you have the intersection of these two distribution that would give you the most likely QPE period that we see.
Right. So we haven't done this full exercise that you're suggesting, but in terms of kind of our understanding of how different orbits are being populated within a nuclear star cluster in steady state, this is something we think we have a reasonable understanding of. So I don't have a slide here to show this,
but it's possible. Okay.
It's possible, yeah. There are definitely
you have
some
to work
uncertainties.
You have to work hard there then.
Touché.
No, I'm joking, sorry. But that's good, yeah, okay, let's chat more about this.
Yeah, we do have, I think, kind of nice results just in terms of considering what will be the eccentricity distribution at the onset of mass transfer, or when this star-disk interaction occurs. There are even some nice analytical results that one can show if you assume something about the stellar distribution within the nuclear star cluster. But yeah, this 0.1 eccentricity is kind of the peak of the distribution. Yeah.
Awesome.
Thanks, Itai. So this is an intentionally speculative question. We know that some white dwarfs have planets and asteroids around them, and we know that at least one neutron star has planets around it. So if you had an accreting binary system, solar mass binary system with planets or asteroids going through the disk, could you produce micro QPEs?
Sounds like a fun paper, but yeah, I think that one perhaps important parameter in this whole model is indeed this question of the effective cross-section of the orbiter and the disk. So I would guess that for tiny objects like asteroids or planets, it will be very hard to produce kind of interesting luminosities.
Yeah, but relative to the size of the object, they're not that small. So anyway,
Yeah.
I think
yeah.
it's unlikely that those objects could survive like an X-ray binary phase. So that probably makes it improbable as well.
Right.
It might be interesting. There's great X-ray timing data. So one could easily search
For
X-ray timing data for large
repeating,
amplitude flares.
Yeah, any sort of repetition, yes.
Yeah, that's true. Vikram was saying there, the pulsar BE star binaries where you see the star.
Yeah, so my question is related to have you speculated or even done some calculation on how the star survives multiple TDEs? My worry is that, I mean, I still don't know the answer. Once the accretion, once the ablation starts, there needs to be a way that shuts it off, so that the star's orbit can keep circularizing.
Yeah.
Otherwise, I mean, it will get destroyed way too early.
Yeah,
so,
I completely agree.
Yeah, what do you think in this direction? Yeah.
Yeah, I completely agree. I think it's not so trivial to invoke a mechanism in which you start ablating the star, but then you pause for a while. I will say that, if you consider perhaps variations in the inclination and maybe the star and the disk align, and then you stop having these destructive collisions, then perhaps, but that would require, I mean, for it to happen on a relevant timescale, I think that would require some fine-tuning for the star to initially be on low inclination relative to the disk, so that would be disfavored on the ground of rates. So we had this paper just like less than a week ago on the archive where we discuss a possible model for this star disk coupled evolution where the star that is not Rauschenberg overfilling but feeds the disk from this ablation, and we show that the disk can then do all sorts of interesting things. It can undergo these instability cycles, so this is thermal instability. We show that these repetitions have typical periodicities of order years to a decade. Part of the motivation is, as I mentioned, to explain these different outbursts that are being seen in GSN 069. But yeah, I mean, possibly kind of one could take this an extra step and also consider the orbital evolution, both inclination and period.
Yeah, I mean, it looks like maybe during one of the dips, then it stops.
Yeah, there's going to be, so the prediction is that there will be kind of phases in which QPEs will be seen and phases in which they will perhaps be too dim or will be outshined by the disk itself. Yeah.
I would say the very non-trivial fact is that the stripping rate of the star is about what we need to explain, the accretion rates in these QPEs.
That's right.
So it's a very nice. you get this lifetime that you present actually quite naturally from Phillips stripping rates.
Yeah,
that's right. Thanks.
All right, Vikram.
Yeah, really cool talk. I was wondering, can you expand a little bit on the factors that might push the emission to the UV? Can you skip past the slide a bit quickly?
The UV QPEs?
Yeah.
This one?
Yeah.
Yeah. So basically, okay, the emission process depends on, there's the shock-heated disk material, but how much mass is in that will generally depend on the disk conditions. So, it's current m dot or, scale height and so on. So if you play with these different knobs, you could change the temperature at which the flare peaks. So in principle, you're not just limited to these soft X-ray flares. I will say that, if you ignore the fact that the disk might be self-sustained by the star itself, so this is this plot that I didn't really discuss, you could imagine that kind of for a TDE-fed disk that you just let evolve with time, the m dot will decay over time, and you'll have a phase where, so this shows where the X-ray QPEs are visible. So this is the flare emission relative to the quiescence for different assumptions on the inclination. And then eventually they'll disappear once the m dot becomes too low. But then after a couple of decades maybe, they reappear as UV QPs. So this is kind of speculative prediction that maybe some of the known X-ray QPEs will eventually disappear and then reappear in UVs.
Sometime in our lifetimes. That'd be amazing.
It will, yeah.
It'd be also cool if the star was destroyed.
Yeah.
All right, let's thank Itai again.